So let's start by talking about content-based and collaborative filtering, two of the most fundamental approaches to building recommender systems. In a content-based recommender system, we make recommendations for a user based only on a vector that describes this user as in a profile or this user's past purchases and the features of the items that this user has purchased. So what's the content of an item or a user? So let's say that we have this example. We have a film that's in the genre of action adventure. It features Bruce Willis and it was released in the year 1995. So these are some features that can describe, for example, a film. Then we can also have other features such as the title or a description or the table of contents in a book, etc. So for example, we can use natural language processing in this case to extract additional features. And in some other cases, let's say audio or image, we have features which can be extracted from the signal itself. So there are features, for example, in the audio, if we're talking about songs, to describe bits per minute of the song or how loud the song is, etc. So the content-based filtering algorithm works as follows. So we accept that each item as well as its user is characterized by a set of features. And these features are recorded in a vector format. So that's pretty much standard, as it happens with all machine learning algorithms. So the simple idea here is that we just have a user vector and an item vector, and we calculate the similarity between the user vector and some item, and we do this through the cosine similarity, and this is the cosine similarity visualized. So if the two vectors, they have similar scores, they point in the same direction, then the cosine will be close to 1, as you can see here on the left-hand side. If the two vectors are unrelated, then in the space they will be orthogonal. So if we're talking about 2 dimensions, this is a 90-degree angle. So in this case, the cosine will be around 0. And if they are pointing in the opposite direction, then the cosine will be close to -1. So let's see an example. Let's say that we have 5 different features for movies which describe the kind of movie. So we have one movie which essentially it's an action movie released in Hollywood. And then the second movie is a comedy and it is a short film. So a user watches movies and then each movie described by a vector. So we can take all those vectors and then average them after a large number of interactions. And we end up with this user vector which describes user preferences. So this is what the user vector looks like. We can see that this guy likes action, Hollywood, and a bit of comedy. So then we calculate the cosine similarity using the formula we saw before. The cosine similarity also, it's very easy to calculate in Python at R. It's a simple function call. And then we get that the user's vector has a higher similarity to the first movie than to the second movie. So we are more likely to recommend the first movie. So let's see another example. Let's say that we want to recommend posts. So a post recommender represents post as a bag of words, and we can average those bags of words from the user's past in order to find out what kind of posts the user likes. So again, if each post is described by a bag of words and the user has read, let's say, 100 posts, we just average this. So when a new post comes along, we can calculate the similarity between this post and the user vector. So content-based filtering has some nice advantages. First of all, you don't really care about having data on other users. You need data only on your user. Also, if you don't have data on your user, you can always ask your user about their preferences. So this means that the recommender system does not suffer from what we call the cold start problem. The content-based filtering also is quite flexible. It can recommend to users with unique tastes. So it's not going to be influenced by what other people like. It cares only about what this user likes. And it can also recommend new and unpopular items. This is called the first-rater problem, that you might have an item described by a vector which matches with the user in a really nice way, and then a content-based filtering system will recommend it, whereas other systems which are based more on user similarity, etc., would need some interactions with these items before they can make a recommendation. Finally, Content-based filtering systems are very transparent. They're easy to understand, since essentially we know why every item is recommended. We can pinpoint exactly the features in which a user and an item are similar in. However, content-based filtering is not perfect. It requires content that can be encoded as meaningful features, and this has to be done manually, so that's not always easy, and it's very difficult if the list of items is very huge and diverse. It's not using information from other users, and also it's easy to overfit. So if a user likes a few items, then the recommender system will essentially always show the same items again and again. Now let's move on to collaborative filtering, which has historically been one of the most successful algorithms for recommender systems. So collaborative filtering was created for situations like the one faced by Amazon, where you have many users and many different items, and the goal is to find items to recommend to this user. So the main idea behind collaborative filtering is that you can use similarity in order to make good recommendations. And there are two flavors: user-based collaborative filtering and item-based collaborative filtering. So in user-based collaborative filtering, we weight all users with respect to the similarity with the active user. So we select a subset of those neighbors to use as predictors, and then we take the ratings they have done for other items, normalize them, and essentially we're saying that, hey, these are the people that are most closely related to this user. This is how they've rated items which the user has not purchased yet. Let's recommend the most highly rated items on average. So how can we measure the similarity between users? Well, we take simply the Pearson correlation. So if two users have rated completely different items, then their similarity is obviously 0. If not, then we take the items that both users rated. And let's say that RA with overscore is a user's average rating. And let's say that RA, P is the rating of a user A for item P. We do this kind of, let's say, normalization in order to get a score here that indicates how above or below the average a user deems an item to be. We do the same thing for user B. So why we do this? Because in some cases, maybe user A likes to rate all items with a higher score and user B likes to rate all items with a lower score. What we care about is not the actual score, is by how much than the average they like an item or how worse than the average they think an item is. So if, for example, a user's average rating is 3 and this user's average rating is 2, then if a user rates an item as 4, this is going to give us a score of 1 here. And if a user rates an item as 3, then again, it's going to give us a score of 1 here. Essentially saying that both users believe that this item is 1 point above their average baseline. So this denominator here is just used for normalization purposes, and we get a score from -1 to 1, which can tell us how similar or dissimilar the two users are. So for example, this is Alice, our active user, and different random users from the database, and we want to calculate the similarity of Alice to other users. So we use the following formula and we get these scores. We get these scores. So we're going to use, for example, user 1 and user 3, which are the most similar, in order to predict what the rating would be for this item, which Alice has not bought yet. So how can you make predictions? You have to calculate whether the neighbor's ratings for the unseen item are higher or lower than the average. That's the first thing you need to do. So this is the formula, and we start with the average rating for a user, and then we have this expression here. So we have B, user B is one of the users which have been selected as neighbors. This is the average rating that user B gives, and this is the rating user B gave for this product. So we have the average user of rating A, the active user, Alice in our case, and then this is the rating that user B gave for this product. And then what we're doing is we multiply this by the similarity between A and B. And we do this for all the neighbors. So this is some kind of weighted average, which essentially is going to be a predictive score for what we believe Alice C would give to this item. And again, the denominator is used as a way to normalize this expression. So in practice, this works quite well, but obviously it's not perfect. There are different ways to improve, First of all, not all neighbor ratings must be equally valuable. For example, agreement on commonly liked items might not be so informative as agreement on controversial items. So we can, for example, give a higher weight when calculating similarity to items that have a higher variance. Also, the value of the number of co-rated items might not be equal across all items. So, for example, we might want to use some kind of significance weighting. For example, reduce the weight when the number of co-rated items is low. So if, for example, two users have 100 items in common which they've rated, maybe we have to score this similarity higher than two users which have rated only 5 items. Also, case amplification is another way to improve. We can give more weight to very similar neighbors. So the weights do not have to be distributed evenly across the neighbors. Maybe we can give an exponentially larger weight to similar neighbors. And finally, in terms of the neighborhood selection, we can either go with a fixed number of neighbors, let's say 10, 20, or 50 or whatever, or use similarity thresholds and say, look, anyone who's above this value is a neighbor. So one user could have 5 neighbors and another user could have 200 neighbors. So these are just some ideas. There are many, many more ideas around collaborative filtering and how to improve it. Item-based collaborative filtering is the other flavor. We saw user-based so far. So the idea behind item-based filtering is that we look into the items that the target user has rated, and we compute a similarity score between all items in our database and the items that the user has rated. We select the k most similar items, and then in a similar fashion to what we saw in the previous section, we calculate a predictive score for the rating based on a weighted average of the user's ratings for past purchases and the similarity of those past purchases to those unrated items. So item-based collaborative filtering was used by Amazon, and it was published in an academic conference in 2001. So it's considered a model-based approach because learning takes place offline for each user, since essentially we have to calculate the scores for each user in an offline manner, similar to the way we train a machine learning model. Whereas for user-based collaborative filtering, we can actually do this process online. The thing with item-based filtering is that it was developed by Amazon because Amazon has this issue of a huge catalog of products, which takes a long time to crawl all of those products and make recommendations for each individual product. And they found item-based collaborative filtering to be a very efficient way for them. So how can you calculate the similarity between products? This formula looks very similar to the similarity between users, but in this case, we care about the similarity for products, not for users. So let's say that you have product A and product B, and you want to calculate their similarity. So you go across all users and you calculate the following: the user's average rating, the user's rating for item A and the user's rating for item B. So that's very similar to the previous formula, but in this case, we're essentially trying to look whether those items are they're being rated as being above average or below average, and by how much. So if both items seem to be 1 point above average for most users, then they're very similar. If, however, one item seems to be 1 point above average and the other item seems to be 1 point below average across all users, then they are dissimilar. So we do this across all users, and this gives us an item similarity matrix. So that's a very useful property in terms of scalability. As I mentioned earlier, Amazon had this issue with scalability for its recommender system because of its huge product catalog. And item-based filtering does not solve the scalability problem in itself. However, there is a way to improve upon user-based collaborative filtering. So one approach which Amazon came up with was to pre-calculate all these pairwise similarities, because this is essentially the expensive part of the computation. And then at runtime, we only care about the items that a user has rated, which makes it way faster to perform recommendations. So whereas the number of combinations might be huge in theory, the number of similarities that need to be calculated, a user might have bought only 10 items, which makes the runtime computations much simpler. Another issue around memory requirements, essentially the number of similarities that need to be calculated, is n squared minus n. So every item against every other item minus the items themselves. However, in practice, this is significantly lower because there are many items which do not have co-rating, so we just ignore them. And finally, there are some other reductions in terms of memory, such as ignoring items which do not have enough ratings or they do not have enough co-ratings, or limiting the neighborhood size. So how do you calculate a score for a new item? Well, that's pretty simple. Again, we have a formula similar to the one we saw earlier for users. We have the score that user has given to item I, and then we multiply this between the similarity of I and product P, where I is a product from the items that the user has rated in the past. So if a user has rated, let's say, 10 similar items to this item in the past, then we take each one of those items, we calculate the similarity between those items and our current item, and we get their rating, and then what we do is we multiply the similarity by the rating and we sum them all up. So in terms of the neighborhood, it looks like, this really depends on the problem, but it looks like in most real-world situations, a neighborhood of between 20 to 50 neighbors seems reasonable. So there are some common issues with collaborative filtering, and those issues are the issues of sparsity, scalability, the cold start problem, and the popularity bias. So the sparsity problem refers to the issue that when we have large product sets, then we're going to have user ratings for only a small percentage of them. For example, Amazon has millions of books and the user might have bought hundreds of books. So the probability that two users that have bought 100 books have a book in common is around 1%. So this means that a standard collaborative filtering model needs to have a number of users comparable to around at least 1/10 of the size of the product catalog. Otherwise, there will not be enough co-ratings. So this relates to the sparsity problem as well. There was this famous competition called the Netflix Prize, where Netflix released some data and called upon its users to improve its recommendation engine. So if you represent the Netflix Prize rating data in a user movie matrix, you get more than 8 billion positions, out of which only 100 million are not zeros. So this is why we have some methods for dimensionality reduction which try to deal with this problem of sparsity, because sparsity is an issue for many machine learning problems, because when you have such a huge data set but the majority of them are zeros, it's difficult for an algorithm to extract the relevant information from the data, because the algorithm will be very predisposed to learning that most of the things in the data are zeros. And in terms of scalability, this was already mentioned in the section for item-based filtering. The issue with collaborative filtering is that in one way or another, you have to calculate the nearest neighbors. So the more millions of customers and products that the company is adding, then this becomes more and more difficult. So the worst case complexity is m times n. In practice, it's more like m plus n, which in any case, it's not as desirable as, for example, the complexity being logarithmic. We have to perform lots of computations, so this can be expensive. And the more successful a business becomes and the more users it adds, then the slower it will become. So there are some ways to circumvent this problem. For example, clustering techniques is one way to circumvent this issue. Another way by using a machine learning model. This is by far the most efficient approach. And finally, two other issues with collaborative filtering is first the cold start problem. That if there are not enough users in the system to find a match, then the recommender system does not know what to do. This is the problem that content-based filtering systems can solve very well. And finally, the popularity bias. So it's difficult to recommend items to someone with unique tastes because the collaborative filtering is based on the similarity between users and items. So content-based filtering is very good in solving these issues.